So the next presentation is by Timo Schweckendiek, and he is also a researcher at Deltaris, and he's going to present to us, I think, that something about his own PhD research.
Right. Absolutely right, Jonathan. Thanks for the introduction. Well, ladies and gentlemen, as you can see, the title of my presentation is Updating Levee Reliability with Performance Observations, and the question that I'm trying to answer is how you can incorporate the information provided by field observations during extreme events, during extreme high flood stages, and how do they affect the probability of piping. So I'm looking at this specific failure mode of uplift and piping. The motivation for this was that, as Ruben mentioned, in the VNK risk analysis project in the Netherlands, recent studies revealed that the probability of piping is actually higher than many people expected. And as we saw this morning in the plenary session, also in the United States, this failure mode is an issue, where they usually call it under seepage or classical backward erosion. That's maybe a more internationally known term. Well, and the two things that I want to show you is actually that you can do this in a rather formal and consistent way using the knowledge that we have about the physics that trigger both the failure but also the observations that we might see in the field. And this is simply by applying Bayesian updating. And I want to show you something about the impact this has on the probabilities of failure. To this end, let me see where this pointer is. To this end, I will start with a short introduction of how we look at Levee's uplift and this piping failure mode into the limit states that have to do both with the failure and the observations. I'm going to show you a little bit about the method, and then we're going to have a look into some specific field observations that you can typically encounter during high flood stages, and then we look at an example from the Netherlands. Now, I don't have to tell you this, but this is more for the general introduction. So that, in protected areas by levees, usually the main trouble occurs when you have a breach and not when there's just overtopping without a levee breach. And this is again to show that there's many failure mechanisms around. The previous presenter has shown a lot more than this, but I'm just focusing on this one, under seepage piping. Now, the way we look at this in the Netherlands, typically in risk analyses, well, this would be the conceptual model for the combined mechanism uplift and piping. You have a relatively impermeable levee with a blanket layer on the land side, and underneath you have a rather permeable aquifer, typically sand. And if you get high flood stages, you get quite high pressures in the sand in this aquifer, which can lead to lifting and rupturing of this blanket layer and cause defects which can act as erosion channels. And then if the gradient in such channels is high enough and the pressures are high enough, erosion can start and you can get formation of those pipes moving towards the river, undermine the dike and or the levee and cause collapse. What are actually the physical ideas? Well, I'm just going to present some very simple ones that we used in the risk analysis, but basically the concept that I will show would be applicable to any kind of even more complex or more realistic physical process-based model that you would want to use. But the main ideas here are that for uplift, we look at the pressure in this aquifer just beneath a critical or a potential exit point, and we compare that to the downward pressure exerted by the weight of this blanket. If the pressure in this aquifer exceeds the weight of the blanket, if you wish, you can get uplift. Heave would describe the start of erosion. So if the critical gradient in this blanket is high enough and higher than a critical value to start moving sand grains, you can get heave. And for piping, typically here we use the model developed by Selmayr, which is an average gradient-based model which compares the gradient or the head difference over the structure to a critical value, or which is modeled by this model of Selmayr, taking into account the soil properties. Now first, before we move to the specific observations, just let me show you and define how we look at the probability of failure in order to better interpret the results later on. The probability of failure would be the probability of having, this stands for uplift, and piping at the same time, because you need uplift, you need a defect in this blanket to get erosion at all, and then to get piping. If you want to update that, you can simply use Bayes' rule, here written as in the form of a conditional probability. So that would be the probability of failure given the observation is the probability of failure and the observation at the same time divided by the prior probability of the observation. In a little bit more formal terms, that would look like this. I just want to focus on this one. Actually, this term would describe the observation. You need some type of inequality, and this also shows that you need the same, some random variables in the observation, in the model describing the observation, need to be the same as the one that describes failure. And then you can get some updating effect. So how would this work with the uplift, heave, and piping models that I was describing before? Well, the simplest thing you can observe during high flood stage is just imagine you have high water levels behind this levee is actually nothing special. I mean, in terms of you don't see any excessive seepage, you don't see any erosion going on. But that actually tells us something, right? Because then we didn't have uplift. In many cases with these high flood stages, we should see some erosion, some excessive seepage going on, else we can at least conclude that no uplift has occurred. But this actually doesn't tell us anything about heave or piping, because that could only occur with uplift having occurred previously. That was the end of the presentation here. Yeah. All right. What if you see excessive seepage? You see a lot of water behind the levee, and that can't be explained by any rainfall event or anything else, and you see the water levels rising. Then somehow you can conclude I must have definitely had exceeded the uplift criterion, the limit state for uplift. I can't say anything about heave, about the start of erosion, because that criterion is a necessary but not a sufficient criterion. Let's not go too deep into that. But it's safe to say that the piping limit state hasn't been exceeded because not even any erosion has been detected. Right? Let's go one step further. If you see heavy seepage and erosion, in terms of our limit states, and when you detect those sand boils here after the event, you can say in that event definitely the uplift limit state has been exceeded and the heave limit state too, because that tells us something about the start of erosion. So in summary, I was talking about three possible observations that you typically make in the field in connection to the three limit state models that we typically use. So for not seeing anything, you would say, okay, uplift has not occurred, no further information. Excessive seepage without any signs of erosion would tell us no uplift has been exceeded, but piping not. And for the sand boils and the erosion part, you would say, okay, uplift and heave criteria exceeded. Now I want to show you how much that can make a difference in the probability of failure if you carry out the Bayesian updating. And I'm going to jump directly to the results. So all the inputs to these examples you will be able to find in the paper. But this is an example which has 4 stratification scenarios, as I'd like to call them, which means that based on the site investigation data, you cannot be sure what the composition of the subsoil, the stratification actually is. So you're working with scenarios and some likelihoods based on the data you have. The probabilities for each scenarios are indicated in this column, adding up to 1. Now here, let's go to this figure up here, which are the fragility curves for the first scenario, just as an example. The medium gray curve here is the fragility curve for uplift, which would roughly tell us, for example, that at a water level, here on the horizontal axis, of about 3 meters, we would have about a 10% chance of seeing uplift, and a very low chance of seeing piping, which would be the black line. And then this light gray line here would represent the probability of failure, which would be the combination of uplift and piping. You can nicely see this is in terms of system reliability, this is a parallel system, because this light gray line will always stay under the lowest value of the other two. Ultimately, here you see the water level distribution. So this would be the distribution of the yearly maxima for this location, which tells us that actually the interesting region is about here. This is actually all above crest levels and not really realistic. Now, and Later on we will see some results, but in terms of the probability of uplift, the probability of piping, of failure per scenario, the contributions of each scenario to the probability of failure. So all right. So the prior value would be about 2 times 10 to the minus 3. Now let's suppose we have an observation at water level 2.8 meters, and let's just see what this would be an about 1 in a 10-year water level which actually occurred at that location. Suppose we hadn't observed anything here, the fragility curves would shift slightly down. So the probability of failure, the conditional one on the water level, would be slightly lower. But these scenario probabilities here shift towards the left side. So in black you have the prior, the likelihood in gray, the posterior in white. And that actually makes sense because that was what I forgot to tell you. The first two scenarios have a blanket layer, an intact blanket layer. The scenarios 3 and 4 don't have an intact blanket layer. So in that case, you would have expected to see seepage and erosion, which is not the case, and automatically in the method, all the probability is distributed to the first two. You have, now let's look at the case where we see erosion and those sand boils. There you see a heavy shift of the fragility curves upwards. Of uplift is this one, and of piping and failure here. And again, you see a redistribution of the probabilities of those ground scenarios, where scenarios 3 and 4 without the intact blanket become much more likely, and the ones with the nice blanket become much less likely, because in that case you shouldn't have seen this seepage and erosion. One last result I want to show is type of result is that you can also, per scenario, you can get the updated probability distributions of the individual random variables. Let's just point out for this erosion observation, the blanket thickness for this first scenario, which should have a blanket layer. Well, if there was a blanket layer, at least it should have been thinner. That's what this graphic tells us. This is the prior, the gray one, and the other one is the posterior. Now just some numbers that I want to show you, not the whole table. This is about to show you that the impact of this changing scenario probabilities can be quite big, which makes, for example, for a no uplift observation where you don't see anything, the probability of failure can go down by a factor 10. And if you see heavy seepage, you see different things changing, but the total probability can go up by a factor 4 for this specific example. So in conclusion, the method I presented is a rather objective and formal method as opposed to others that are out there that are purely based on expert judgment, and it helps you to incorporate the information provided by field observations. The probability of failure can change roughly by a factor of 10 both ways. Again, this was just one example, but you can imagine that this was not a very special one. The more surprising an observation is, the more significant the effect, right? So the less likely, for example, observing erosion was, a priori, the bigger the changes are from the prior to the probability. So what I hope is that I could encourage you to use such kind of methods to incorporate field observations in your own reliability analyses, and I'm happy to answer any questions if there's time.
Thank you, Timo, very much. We are pretty much out of time, actually, but if there's a burning question, then I'll take the lady over there. Maybe just quick.
I just have a question concerning the observation cases. How many cases did you include? And as I know, if you have the case that there is a seepage, normally you will take countermeasures and not only observe it. So it will just spoil your statistics a little bit, I think.
Yeah. So in this case, this would be only one observation at a time. So I would only observe one event, and the changes that you saw were based on one event. To the second question, if you take countermeasures, I left it out of the presentation because already over time, obviously. But since we're not looking at the piping limit state, maybe we can discuss this in detail later, but that wouldn't make any difference for the 3 types of observations and connected limit states that I was looking at, because it's about the start of erosion, not about the, let's say, the failure afterwards. Yeah.
Okay, thank you very much indeed.